Hi everyone, thank you for being here today, even though it's virtually. I'm Scott Freitas, and today I'll be talking about our work, Unmasked, Adversarial Detection and Defense through Robust Feature Alignment. Let's start by discussing what is an adversarial attack exactly. On the left-hand side here, we see a typical image of a train, which any kind of deep neural network would look at. In the middle here, though, we see the same image, but now it's been perturbed by an attack. In this case, projected gradient descent, and quite a strong attack at that, epsilon equal to 32. Essentially, what's happening here is now this attack is modifying this train image so that the classifier no longer sees a train. It fools it to thinking there's something like a bird there, or a person, something very different from what the object is actually there. And on the right-hand side here, we see the actual pixel difference between the attacked and the benign image. We can see there's been many pixels modified. However, when a human looks at this middle image, we still see the train essentially. Something very different from what the model's actually seeing. So let's talk about the landscape here a little bit. So the adversarial landscape is actually evolving quite rapidly. In just 2020 alone, there's over 1,000 papers published in the adversarial landscape. So this highlights the importance of the attack and the defense landscape and how we need to keep developing new defenses to keep pace with all the attacks coming out there. Unfortunately, the attacker has a significant advantage in this process. While the defender needs to protect against everything, the attacker only needs to find a single weak spot. So we call this the defender's dilemma. Essentially, while the defender has to maximize model accuracy and robustness, they have to simultaneously protect everything while the attacker only needs to find a single weakness in the defense. So it's been shown that traditional defenses like adversarial training are very effective, but also quite expensive to train and often lowers the model accuracy, which is not good in the settings where a large proportion of the images you're looking at won't be attacked. They'll be just traditional benign images, and we don't want to lower the model accuracy when we don't have to. So there's been some interesting work that shows that robustness is a function of the data, essentially. And so what's this mean? It means that essentially there's adversarial examples can be attributed to non-robust features. And we might ask, what is a non-robust feature then? These features could be something that's not really aligned with human intuition, it turns out. So when we look at a picture of a dog or a cat, a human sees the robust features, we'll say. We see the tail, the head, the torso, the legs, but the classifier sees those and other features which humans don't typically pick up on, which they can be patterns in the pixelation essentially. And so it's interesting that by only training on the robust features, it's actually significantly worse than training on all the features. So this shows the predictive performance of the robust and the non-robust features. However, these non-robust features come at a cost that they can be perturbed and allow the model to misclassify things when attacked or perturbed. So what's the solution? We propose Unmask, which essentially has the goal of maximizing model accuracy and robustness simultaneously. However, our solution is to separate the defense from the traditional classification process. We do this by training a benign model on robust and non-robust features to maximize accuracy, as would be traditionally done. And then at the same time, we have a second model which only trains on the robust features, allowing us to then determine if the predicted class matches the observed robust features of the class. So this goes back to what we were just talking about, where essentially if a dog is the predicted class, but we're saying it's actually a train, which is what the human sees, we can see the robust feature difference, and which is something we're going to talk about coming up here extensively. So here's an overview of the Unmasked pipeline, and we'll cover each part in detail, but let's give a high-level overview to start of each section. So on the left-hand side here, we can see an image of a bicycle, and it's been attacked, and essentially now a model, which becomes on the left-hand side, is going to see this image, and it's going to predict it's a bird. And obviously, a bird has the features seen on the bottom right. We can see that there has the beak, the eye, the feathers, the legs. And then when the same image goes through the object detector, we can extract its robust features. So these features aren't being perturbed, it's just typically the class label that's being perturbed. So what we see here is the wheel, the saddle frame, the handlebar, the pedals, and we can extract these features out. And then we can compare these extracted features with the expected features of the predicted bird class, and we can see there's not much in similarity. And we can use this essentially to rectify it and detect the misclassification. So now we're going to talk about each one of these processes one by one, starting with the image's robust features. Essentially, we can consider these the bike's building blocks. It has a wheel, the frame, and the seat, and these are something that aligns very closely with the human intuition. They're human comprehensible, as we like to say. Essentially, this will form the foundation for our adversarial defense process. So how do we obtain these robust features? So we use a mask RCNN trained with segmentation masks on all the robust features we want to collect. And there's one mask per robust feature and 44 robust features. So for the running example here where we have, the bike would have the wheel, the seat, and the frame, and those would compose some of the robust features of the bike. Okay, so now how do we actually use this process for detection and defense? So we see the extracted robust features on the bottom via the segmentation masks. We have the wheel, the handle, the seat, and then on the top we had what the model was predicting, this bird, which essentially we know what a bird should have in terms of its expected features. It has the head, the claw, the wing, and the tail. So now we can compare these expected features of the bird with the extracted features, and essentially we can see that there's no similarity between these feature sets. And this would indicate that yes, this image is under attack, and then we can essentially reclassify the image, and the prediction is actually a bike. So let's talk a little about the experimental setup here and some of the data sets we're using. So the building block extractor essentially is the mask RCNN. This is going to get the robust features from the image. We trained this using a feature pyramid network and a ResNet 101 backbone. And essentially we're using the Pascal part dataset to train and evaluate the effectiveness of the robust feature extractor. For the traditional CNN models, which we call the vulnerable CNN models because essentially they have no defense here right now in the setting, we trained them on the Pascal VOC 2010, which we chose to align with the Pascal part dataset because they have the same classes, except for Pascal part has also the additional segmentation masks on the robust features we want. And for those vulnerable CNN models, we use the popular ResNet 50 and DenseNet 121. And then for the detection and defense, we evaluate the performance one-to-one with the vulnerable CNN models on Flickr data, which we scraped from online. And we create this new data set of novel images that have never been seen, matching the same classes from Pascal VOC 2010 and Pascal part, allowing us to have a one-to-one correspondence here. So we evaluate, in this experimental setup here, we also evaluate 4 adversarial attacks: PGD L infinity, PGD L2, MIFGSM L infinity, MIFGSM L2. In addition, we also look at the very important concept of feature overlap. So essentially, feature overlap is going to look at how many features are similar between the different class sets we want to evaluate. So let's take an example here. CS3A and CS3B both have 3 classes, but they have very different number of unique parts. So essentially what this means here is that CS3A has very distinct images like a human, a train, and a car. And this adds up to many unique and distinct parts and low feature overlap, while CS3B has the same number of classes, but a much higher feature overlap. So this could be something like a dog, a cat, and a person, and this is contributing to very similar features. And then CS5A and CS5B repeat this similar process, essentially to CS3A and 3B, except for with 5 classes. Okay, so now let's talk about some of the experiments for detecting attacks that we ran. So the goal here is to evaluate whether or not we can detect adversarially perturbed images from benign images. To do this, we have a 50-50 ratio of benign to adversarial examples, and we look at these different class sets. So on the side here, we see the picture of the ROC plot. And what we see here on the top left is the dark blue line here. And this dark blue line is CS3A. And as we would expect here, this performs the best with the low feature overlap, which essentially indicates that feature overlap is an important measure here to look at. And even more interestingly here, we can see that feature overlap actually plays a more important role than the number of classes. So CS5B in the light orange actually outperforms largely CS3B. So which this indicates is that feature overlap can actually override and be more important than the number of classes. So you can have a large number of classes as long as they're have distinct features. And we think this is actually pretty reasonable in many settings, because if you're looking to do object detection for safety reasons, it may be more important to determine the general class of the object rather than the distinguishing if it's a dog or a cat per se. So let's see a couple more examples here. Essentially, we're going to look at the PGD and then the MIFGSM or MIA. And what we see here is that the detection is actually rather agnostic to adversarial attack strategy, meaning that these robust features work well across a variety of attacks. And this is pretty important here, because it indicates that these attacks are really attacking the class label, not the individual features of the image. So the second part here is countering the attacks, whereas the first part was essentially detecting them. So in this part, we're looking at how well we can reclassify these perturbed images. So these images are all adversarial by nature, 100% contamination rate, so to say. And some of the things here we want to highlight is that Unmasked does better with less feature overlap, as we were discussing earlier. And this can actually be more important than the number of classes once again. So by comparing the CS3A and the CS5A and the blue lines here, we can see that essentially Unmasked performs better when there's lower feature overlap. And this is, as expected, essentially the distinct features help distinguish these model or the images better. So a second interesting finding here is that Unmasked is independent of neural network architecture. So we can see here comparing essentially the CS3A and the CS3A of the ResNet and the DenseNet, which is the blue to blue, and then the pink to the pink. We can see here performance is very similar across models, which is to be expected essentially. And then the final interesting thing here is when we compare Unmasked and how it performs to no defense and how it performs to adversarial training on a whole when we average it across all these different class sets essentially. And then we find on average Unmasked performs about 26% better than adversarial training, and then 77% better than no defense in the CS3A, and then we can see the different performance improvements across these different class sets. So there's a few directions for future work here which we think are important to look at. And the first one is to attempt to break this defense with attacks on the mask RCN itself, essentially. So we need to break the underlying mechanism in order to reduce the classification accuracy of the whole system. And then the second part is to reduce the dependency on the segmentation masks themselves, which are expensive to annotate, essentially. So these form the two directions of future research we're looking at right now. Alright, that's it everyone. I want to thank you for being here. If you have any questions, please feel free to reach out to me. You can find more information on the paper on my website, scottfreitas.com. Thank you very much, everyone.